remember what a schematic is for? A schematic is really just for showing how a component is logically connected to another component. It does not really show how the traces, should look like. In this case, the output of pin 3 of the 7805 has to connect to VCC of the MCU. When you draw a line, it is actually not called a line. This is called what we call a net or a node in electrical circuits. You press the lowercase n key to start to draw a node or a net, and then you just extend it to the other pin like that. And then you just click, and you can also press the you can right click to stop the drawing. So now we have one connection. It's kind of faint in blue. It's kind of like a dark blue line. It represents a net connecting from pin 3 of the regulator to pin 52 of the MCU in this case. So logically, we understand now that pin 3 of the regulator connects to pin 52 of the MCU. It is not limited to only one pin to one pin, because all of these are VCCs, so you can actually start to draw another net to also to go to pin 21, kind of like that. Okay. Are there any questions? The big dot on the screen, I can show you right here. This big dot here is representing that these two lines are not just crossing each other, they are actually connected to each other. Any questions? Yep.
So the voltage regulator doesn't supply the power, it just tells the power where to go?
It's a regulator, which means the input can be like 7 volts, 8 volts, 10 volts or so. The output stays constant at exactly 5 volts. Okay, good question. It limits the current by dying.
Yes.
When you try to draw too much current, the regulator will die. It will just it will heat up and die.
Still better.
You can always put a fuse in the system, which is the better way to do it. Okay, the input or pin 1 of the regulator typically would go to the positive terminal of your battery. Okay, and your battery, have to have at least 7.5 volts, because there's a 2.5 volt drop at the regulator, and that's something that you cannot control, because it has to do with the type of device that we are dealing with here. Now, pin 2 here on the regulator is what we call the ground pin. The ground pin is a reference pin for the entire board. This is where we measure 0 volts. The entire board needs to share one single ground, where the voltage measured voltage is 0 volts. Okay, without taking any physics classes, it's a little bit harder to explain these concepts, but we'll go ahead and do it anyway. So now I have just drawn another net going from pin 2 of the regulator to pin 22 of the MCU. When you're doing schematic capture, it's just doing this all day long. You put components onto the schematic diagram, and you draw the lines connecting the components, or connecting from one pin to another pin. Any questions about this part? It's all kind of graphical, but to get used to the software, sometimes it can take some time. Okay. To use a regulator, you also need to use bypass capacitors, and a bypass capacitor is like suspension of a car. In other words, when the MCU suddenly needs to draw a bunch of current, the regulator cannot supply as quickly as the demand. So you need a capacitor to be sitting there between pin 3 and pin 2, so that when you have a sudden increase of demand of current, the capacitor can discharge and satisfy that particular requirement. So we can also do the same thing here. We can just we can pick a capacitor, and there are many capacitors here. They are all listed under basic devices. So under basic devices, we have a selection of capacitors to use. The different diagrams. Yep.
Oh, I was just. This isn't really like a question. I was wondering if you had like a schematic that's already completed? Because I'm having trouble seeing this in a big picture setting, like how like where these components would be in a completed circuit.
Okay. I can show you finished products too. Let me put this in, and then we'll talk about the.
It's like a map.
Yeah.
It doesn't really matter.
Okay, let
It
me
doesn't matter where it is, but it does matter how you connect it.
let me get out of this one, and I'll save it as.
Right.
We'll just say arcdev 1 as an example.
That's it. And point B could be able to be in point A could be able to be there.
Okay, this is something that I did, in the summer because I got nothing else to do. It is actually a product, or it's a controller board for my consulting job. It's not really complicated, but it has a lot of the interesting components. You can see this is really just a big map of these components. And let me just kind of zoom in to this part here, because that's the regulator circuit or sub-circuit. This is the input. Okay, these 2 points represent the input of the entire system, the power input. It goes through a diode first, okay? Just in case someone decides to try to hook it up backwards, the diode will protect the circuit, so the rest of the components, including the diode itself, will not blow up. Okay, without a diode, if someone plugs it in backwards, a bunch of components will die painfully. C11 here is what we call a bypass capacitor. 47 microfarad is the specification. This is a unit to measure capacitance. And here we have L2, which is an inductor. C11, L2, and C5 combined is called what we call a pi filter. In other words, when the input power has some high frequency noise that's fluctuating, this will help so that by the time it gets to pin 1 of the regulator, that noise will be smoothened to the point that the regulator can handle it. Because I found that without this type of filtering circuit, the previous design was not very reliable because of the noise issue. This thing has to switch a lighter on and off.
So it's really,
It has a lot of fluctuation because of that. And then we have the regulator here. It is only specified as a 7805, and then the output capacitor is C6, which is also at the same value of 47 microfarad. When you design a circuit board, it is usually good to reuse the same type of components over and over again, because when you order the components in larger quantities, they get cheaper. So sometimes, even though I don't really need a 47 microfarad cap here, it is actually less expensive to specify this cap because I can now order, in a larger quantity and therefore get a better discount. F2 is a fuse. It is specified at 500 milliamps. In other words, the fuse will blow, if the current is sustained at more than 500 milliamps. It's always a good idea to put fuses throughout the system, so that if one component fails, the fuse will blow first, and by diagnosing which fuse was blown, it gives you an idea of what went wrong on the circuit, with the circuit board. This is a diode, and it is called LED1. LED1 is nothing more than, yes, power is good indicator, because all it does is to hook up to the output of the regulator. As long as the regulator is outputting healthy voltage, this LED will be lit, just to say, yes, we got good power. Because sometimes, when your circuit board is not working, you don't know whether it is not getting power or the rest of the board is not working for some reason. Okay. And here, this one is kind of important. I put a name onto a net. This one is called VDD. This means that throughout the schematic, if I connect something to a net called VDD, it is logically connected to this particular node on the circuit. This makes it possible so I don't have to draw lines all the way from one end of the schematic to the other end of the schematic, because the name of the net implies which electrical node I'm talking about. It's basically the use of variable names in a program. Okay, by spelling out the name of the net, I can just refer to the name of the net instead of actually drawing a line all the way over to every single point I need to connect to VDD. Are there any questions at this point? I mean, no? So I won't bore you with the rest of the circuit board, because this one has a whole bunch more stuff. Yep.
Does the software determine how much amperage the whole circuit uses, or do you have to do that by yourself?
That's the application of the circuit, because in this case, let me zoom out a little bit so you can see a little better what I'm talking about. Okay, this particular circuit has it has a whole bunch of MOSFETs. Okay, it has an array of like 7 MOSFETs, and each one is used to drive a solenoid or an air pump, a small load. So this one actually is going to consume quite a bit of current, but not at 5 volts. The 5-volt rail is only used for the processor and other logical components, but it's not used to drive any type of power components. These are all driven directly from the power input itself, and not from the it's not post-regulation, it is pre-regulation. Okay, and this is also a diagram showing you that this design has a flyback diode. A flyback diode is basically a device so that you can use the low side drive circuit with an inductive load. An inductive load is basically any component that has a lot of wires in the inside, like motors, solenoids, relays, and stuff like that. Without a flyback diode, it will fry the transistor in no time. Basically, spark plugs. You don't want spark plugs except in the engine. You don't want a spark plug on the PCB. Yeah, it's called a flyback. Yeah, it's called a flyback diode, so that the current has somewhere to go. And when you take that physics class, you will learn that when a magnetic field is collapsing, and you have wires around that can be influenced by the collapsing magnetic field, it will induce a current on the wire, and that current will go regardless of the resistance. It will generate as much voltage as necessary to keep the current going. And sometimes it can go all the way up to tens of thousands of volts inside your car's engine, and we call it a spark plug. Not too many places need a spark plug. Most circuit boards do not. Okay, so let's look at some of the other components. Oh, well, this would be a good one to take a look to. This part here, or connector 3, is really just a connector. That's all it is. It represents an actual row of pins on the circuit board, and this is how I represent how each pin of the connector is connected to the rest of the board. It is all done by name, because I don't want to draw lines all over the schematic. The names makes it so much easier to represent and say this pin is logically connected to that pin over there that has the same name, or the net connected to that has the same name. Okay, are there any questions about schematic capture? So at the end of the entire schematic capture process, you end up with a relatively big design, kind of like this here. You specify all the components, all the pins, how they're supposed to